Hello, I'm Chris Potts. This talk is called Finding Linguistic Structure in Large Language Models, and it's for the 2025 annual meeting of the Linguistic Society of America. The central claim I want to make in this talk is that large language models, LLMs, can be useful tools for doing close linguistic analysis. And I think the best way to go about trying to persuade you of this claim is via a detailed case study. And for that, I've chosen the English Preposing and PiPP construction. I'm going to call these PiPP constructions. They're a longtime favorite of mine. Here are a couple of examples. We decided not to pursue it, incredible though it seems. The clause in maroon is the PiPP, in this case headed by though. We also have variants that are headed by as, incredible as it seems. And the most frequent variant is also the most unusual in some sense, as incredible as it seems. That's an as-headed variant with an extra adverbial as at the start. I'm guessing that these PiPPs sound unusual to many of you, and you might be wondering whether you use or even encounter them. I suspect you have, but this is still an interesting intuition, because I want to say that PiPPs are incredibly infrequent, and let me actually quantify that a little bit. I did 2 frequency analyses. The first was in the open books corpus, which is about 18,000 self-published books amounting to about 90 million sentences. And I estimate that the frequency of PiPPs in that corpus is about 0.03%, a tiny, tiny number. I did the same kind of frequency analysis in C4, which is the colossal clean crawled corpus. That's much larger at 365 million documents, about 7.5 billion sentences. And their PiPP frequencies are arguably a bit lower, although I'd still call them about 0.03%. As I said, those are tiny, tiny numbers, and to put them in context a little bit, I estimate that 12% of C4 sentences contain a restrictive relative clause, making restrictive relatives about 400 times more frequent than PiPPs. So that gives you a sense for how unusual PiPPs are in actual usage. I do think it's noteworthy that their frequency is a bit higher in the books corpus. It's in literary construction intuitively, but across the board, it's highly infrequent. There isn't much literature on PiPPs as far as I know. The most detailed treatment that I know of comes from just a few pages of the Cambridge Grammar by Huddleston and Pullum. That's an incredibly empirically rich treatment despite being very short. And basically I'm going to walk you through some key highlights of that treatment and hope to add some value with a few more interesting examples. There's also a discussion of PiPPs in Ross's thesis. I'm going to return to that. And Peter Kulikover has a paper called Though Attraction. So those 3 things are the work that has primarily shaped my understanding of the construction, together with a lot of work with corpora. So let's dive into the details a bit more. This is my proposal for the core structure of PiPPs. I'm happy to negotiate the node labels with you all. The first core claim I want to make is that PiPPs are indeed headed by this preposition here, which has to be though or as. The second core claim is that PiPPs are long-distance dependency constructions. And I've indicated that here with the co-indexing of the preposed phrase up in the upper left, incredible, with that pred-comp gap down in the lower right. The relationship between these 2 positions is complex, as we'll see, but there's undoubtedly a long-distance link between them. All right, let's run through some of the core properties of PiPPs, starting with the simplest one, the prepositional heads. As I said, these are limited to though and as. Here are a few attested cases. That disaster, bad as it was. And the C here indicates that that's an example I found in the C4 corpus. And the B here indicates a books corpus, young though he was. Now, a striking thing about PiPPs is that even semantically very similar prepositions like although and while do not participate in the construction. As far as I can tell, it's ungrammatical to have things like that disaster, bad although it was. Also unusual for PiPPs is that when as appears in the construction, it can have both an additive reading and a concessive reading. The additive reading is kind of expected given the usual semantics of as, but the concessive reading seems to be entirely constructional and in fact closely related to what you get if though is the head. Happy as we were with the proposal we adopted it, that's an additive reading of as. Compare that with happy as we were with the proposal we couldn't adopt it. That's the unusual concessive sense that, as far as I know, occurs with as only in the PiPP construction. All right, let's think about gap licensing. We're going to focus here on the head down here. In this case, it happens to be a verb licensing the PiPP gap, but lots of things can be licensed, or It's probably all the things that can take property denoting expressions as their complements. So be, seem, appear, feel, look, sound. You can also get resultatives, complements to modals, complements to do. There are also some adverbial cases. It's harder to see how licensing works for them, but they are robustly attested. And here are a few examples just to flesh out this summary. That recipe nags me still, perfect though it tastes. Their tastes is the gap licenser. Busy though they kept us, I was quite bored. Here's a resultative. Clean as they wiped the table, I still worried about germs. Here's a modal licenser, try as he might. That's actually one of the most frequent variants of PiPPs. There are thousands of that locution in the corpus data I've looked at. It's a sure thing that you've heard them before, perhaps without even noticing that they were PiPPs. Peer though I did, that's another verb phrase case here with do as the licenser. And as I said, examples like 12 are trickier to work out in terms of licensing. Much though I want this to be in Kashmir, I don't know what is acting as the licenser for the preposed adverbial there. But as I said, these are definitely possible. Largely set them aside going forward. Let's move now to the preposed phrase. And here my generalization is simple. Anything property denoting can appear in that preposed position. But there are some twists. So we can have things like verb phrase as in tempted to run though he was. We can have predicates like few though they might be. Struggle though he might, that's a verb phrase case. You can also get noun phrases. This is an example that was found for me by Brett Reynolds. A high crime neighborhood though it was. And this example is actually noteworthy just because for my intuitions and experience, the most frequent variant when you have a noun phrase in this position lacks its determiner. That's things like withered thing though it was. That's a mismatch with the corresponding regular prepositional phrase. You just don't get things like though it was withered thing. But for PiPPs, the determiner can get dropped, and I actually think preferentially it does get dropped, making the shape of those noun phrases quite unusual. And then finally, as I said, one of the most important properties for the discussion today is the observation that PiPPs are long-distance dependency constructions. Here's a simple case, incredible though they said it seems. That's a case where this gap spans one finite clause boundary. The observation that PiPPs are long-distance dependency constructions traces at least to Ross's dissertation. Ross has a whole discussion of PiPPs, and he offers very colorful examples like, handsome though everyone expects me to try to force Bill to make Mom agree that Dick is, I'm still going to marry Herman. As usual with Ross, it's an endearingly funny and quirky example, but I think we all recognize that it's fully grammatical as a PiPP, and in this case it spans 3 infinitival clause boundaries and 1 finite clause boundary. Outside of its inherent complexity, it doesn't strike me as all that strained, and outside of its quirky content, I actually don't find it odd. And here's the point, I find that absolutely amazing. It is amazing that I, and I hope we, find the example to be pretty unexceptional. And here's why. PiPPs spanning finite clause boundaries are vanishingly rare in our actual experiences with language. I first became aware of this when Jeff Pullum issued what I'm going to call here Pullum's Challenge. This was in the year 2000 when I was just starting graduate school. Jeff was teaching a math linguistics course for us, and he and Rodney Huddleston were deep in the process of doing the Cambridge grammar. And I think they were trying as much as they could to rely on attested examples to build up the arguments in the book. And I infer that they were having trouble finding PiPPs that spanned finite clause boundaries. So in class one day, Jeff issued this challenge/opportunity. $1 for each naturally occurring PiPP spanning a finite clause boundary presented to him by the very next week of the seminar. Now, I had a good habit at the time of collecting examples that caught my eye as I was reading and experiencing language, and I had a few PiPPs in my collection. The most unusual one that I could find at the time was, hungry though I am for life as the next fellow. When I recorded this, I didn't know much about PiPPs. I think I jotted it down because of how unusual it is, and that again speaks to the fact that PiPPs are very rare constructions, and this is indeed a rare configuration for them. Jeff gave me a nickel for this example, which was nice of him. It's not the kind of example he was looking for, so there was no dollar forthcoming at the time. But I kept looking, and I soon discovered that PiPPs are common across infinitival boundaries. That would be cases like mild though he knew himself to be. It's easy to find those. but I found it's very, very difficult to find examples spanning finite clause boundaries. It wasn't until 2 years later that I found one for myself, philosophical and unscientific though he knew they were. And I breathlessly wrote to Jeff to brag that I'd finally found an example. Jeff continued to enlist people in his quest to find such cases even after that. I think he enlisted Mark Davies, who found one for him in Coca in 2009, good though he knew it was. And then it wasn't until 2011 that Jeff found his own case, unpopular though I can well see that it might be. 11 years is a long time to find an example, but in fairness to Jeff, this case is noteworthy because it was a case of spontaneous speech. Jeff heard it on BBC Radio 4 and he could tell it was unscripted. So congratulations to Jeff on finding an example. This, though, begins to give you a sense for how rare it is to find these long-distance cases, right? It took us so long to find these few examples. But I wanted to make that a bit more systematic. So in the summer of 2023, in preparation for an event in Edinburgh celebrating Jeff's life and his career, I used all the power of modern NLP. Classifiers, language models, regular expressions, parsers, corpora, everything else, to try to find some PiPPs spanning finite clause boundaries. And trust me, this was a heroic effort. And at the end of this heroic effort, I had found 58 cases spanning finite clause boundaries in the massive corpora that I mentioned before, books, corpus, and C4. The gems of my collection of those 58 are the 3 that I found that actually span 2 finite clause boundaries. I'm proud of this, so here's one of the examples from C4. Well-intentioned, though many people may have imagined that the CIA probably thought they were. And I have exactly 2 others like this, both of them headed by as. I'm happy to report to you that Jeff bought me dinner as a reward for these cases, even though I was almost a quarter century too late in producing them. But I'm very proud of all of this. So let me kind of summarize the generalizations that I've offered so far and also bring out some high-level points of all of this. So this is the picture of PiPPs again. And the core claims are first that the head has to be though or as. That's very restrictive. Second, the preposed phrase can be anything property denoting. That's very permissive. And then we have 2 quirks. You can get missing determiners when there's a noun phrase in that position. And we also sometimes get that surprise as adverbial in cases like as incredible as it seems. The gap position generally needs to be the complement to something that selects for a predicate. And finally, PiPPs are long-distance dependency constructions. Great. First, this is a highly refined and nuanced picture. It's flexible in some places and it's rigid in others. And we learn all this despite the frequency of these constructions being vanishingly small, just 0.03%, as I said. And what's striking is that these generalizations also pull in 2 different directions. For the prepositional head constraints, our actual experiences exhaust the possibilities. We experience PiPPs with though and as the head, and we conclude that those are the only possibilities for the construction. For the preposed phrase, things go in the opposite direction. We experience a tiny number of expressions as preposed PiPP phrases, and we conclude from the tiny number of experiences that anything property denoting can appear in that position. And the long-distance dependency thing is like the preposed phrase thing. We have a small number of experiences with these dependencies, mostly with single clause cases. And yet those experiences suffice as evidence for us for the possibility of multi-clause long-distance dependency PiPPs. This is a marvel of a situation, right? And for the rest of this talk, I just want to help us make sense of this through the lens of large language models. To do that, I first need to review just a few basics of LLMs. We don't need much for this talk, so I think we can do this efficiently. The first core notion concerns how LLMs are trained, and the core idea here is self-supervision. We're going to teach the model to learn to imitate the sequences it's trained on, and that's it. So imagine we have the train sequence start token, the men in the room. We feed that into the model. Here I've got the model depicted as a gray box. This box actually contains a vast ocean of numbers, which are called the parameters. And the point is that those parameters for now are set randomly to start. We would like to teach the model to reproduce this input sequence, but since it's a random model at the start, it just produces a random sequence as output. And here I've imagined that it predicts the sequence consisting only of the. So this looks bad, but we have an asset. We wanted the model to predict the input offset by 1. So start token should lead the model to produce the, and then start the should lead the model to produce in, and so forth and so on. It didn't do that, but we can use the distance between the actual and predicted sequence as an error signal to update the parameters to make it a little less random. So maybe we do that a few million times, and then the next time we process the sequence, the results are a little bit better. Now it says the men run fast and. We again compare that prediction with the actual sequence, and that gives us another update to the parameters. Again, repeat that a few million or billion times, and maybe now the model is in a state where it makes the desired predictions. In practice, models are trained like this on corpora as large or larger than C4, so vast oceans of data. And the core thing, the major scientific discovery, the thing that is so magical and weird about this moment with LLMs, is that models trained in this way learn an incredible amount about the causal properties of language just from this imitative self-supervision learning. All right, that's training. We're going to make one more use of one more property of these models, and that's the way that we can use them to estimate the probability of different continuations. So here's our trained model again, and it's about to generate a token. Whenever the model generates a token, what it actually does is produce a probability distribution over the entire vocabulary at that time step, at each time step. And so that could be over 50,000 items, depending on the size of the vocabulary. Here I've just shown a few of the vocab items. And we might in fact decide to focus on the fact that the model in this case has more probability on are than is, because we might take that as evidence that it knows in some sense that agreement is with the head noun men and not the closer noun room. But let's not get ahead of ourselves. There's one more important fact about LLMs that we need going forward, and that's that their representations are organized into a grid, as you see here. The largest models we're going to look at today have actually 21 layers like this, and for them each of the boxes is a numerical representation which is about 4,000 numbers long. In addition, the lines that you see connecting the boxes across layers have a left to right processing structure. When we generate a new token, left to right, the model can look to the entire past, but it can never look to the future. That's called an autoregressive language model. All told, the language model in this talk, the largest of them, has about 6.9 billion parameters. For us, though, the main thing is not the size. What we're going to do is look at these boxes. It turns out that these boxes, these numerical representation, encode a lot of very rich, highly structured linguistic information, and that is in fact an explanation for why they are so successful at so many linguistic tasks. And in fact, let me move now to substantiating that, first with a few background constructions and then with PiPPs. To begin this section though, I just wanted to give a few shout outs to some really influential papers that have shaped the results in this talk and my thinking and really opened up new avenues for investigation. I want to say at a high level that the area of literature that I'm engaged with is one of the most vibrant and exciting areas of research in all of science. It is full of creative people doing very ambitious things. I'm only going to touch on a tiny number of these things. I find this, though, an incredibly exciting community, and I would love it if more people from the LSA were participating in those discussions over in the world of the ACL, because I think everyone would be enriched by those truly interdisciplinary contributions and interactions. But my time is limited, so I wanted to highlight just a few papers that are really influential for this talk, beginning with Tenney et al. 2019. This is one of the first papers that probed language models for rich linguistic structure, and they found a lot of very suggestive evidence that models are encoding many aspects of linguistic form and meaning and everything else at different levels. It was very ambitious for the time. I think they were met with some skepticism about whether this would work out at all, but they persevered, and I'm confident that I wouldn't be giving this talk today without that kind of groundbreaking thing that they did. Now, the methods that I'm going to focus on are in many ways descended from Tenney et al.'s probes, but they're also rooted in the literature on causal inference. And in that context, I'd want to shout out Vig et al. 2020. They did causal mediation analyses of neural models. And in that, they pioneered aspects of the intervention-based approach that I'm really going to advocate for in a moment. And then we get some specific linguistic phenomena. Marvin and Linson is a quite early contribution in the area of targeted syntactic evaluations with LLMs. They helped us see that language models are learning very rich theories of agreement, among other things. And then Wilcox et al. 2018 and 2023. The second one is a paper in linguistic inquiry, and these papers make a very persuasive case that models are learning something rich about filler gap dependencies, and that's of course really central to what I'm about to present. Mahowald 2023 and Mishra and Mahowald 2024, these are striking and ambitious contributions that show that large language models have learned a lot of intricate things about very rare constructions. So Kyle and Kanishka really inspired me to do the work I'm reporting on today. I don't think I would have undertaken this project otherwise without their pioneering contribution. And then finally, there's a whole series of really ambitious and interesting attempts to create benchmarks so that we can quantify the extent to which models have learned various aspects of form and meaning in language. COLA is one of the first of these. COLA is from Warstadt, Singh, and Bowman. It's the corpus of linguistic accessibility, and I love this. Sam and his collaborators included COLA in the GLUE benchmark, which for a time was the most widely used benchmark in all of NLP and kind of in all of artificial intelligence. And so they in effect got that whole world of researchers to care in some sense about minimal pairs and fine-grained grammaticality judgments. I regard this as quite a coup. Blimp and Syntax Gym and Causal Gym followed, and we now have a bunch of others in this space that are focused on other languages and other phenomena. And as I said, this is just a small sample of what's happening in the world of the ACL and NLP and everything else. Incredibly exciting, ambitious linguistic research. I think the number of publications shows that the community values this kind of deep exploration. And I also want to say that I think these papers are disproportionately winning best paper awards at those conferences. Kanishka and Kyle won one of the top prizes at the most recent ACL meeting for their work on unusual constructions. And Causal Gym also won a top award last year. I think the NLP people like to talk about themselves as pure engineers, but in their hearts, they are scientists, and they tend to value deep scientific contributions like what we're getting in the papers I just mentioned. For the experiments I'm going to report on today, I'm using the Pythia series of models. This is an amazing open source project that has really taught us a ton about language models and how they learn to represent things. Models in the Pythia series come in sizes ranging from 70 million parameters to 12 billion or so. They're all autoregressive language models. That means they have the left to right structure I showed you before. They're fully open source and open weights. We know exactly what data they were trained on. There is no instruct fine-tuning. That is, they were trained purely in the distributional mode I described before with no other forms of supervision about what counts as good or bad. And I won't get to discuss this, but one wonderful thing about the Pythia project is that each one of these models they released many checkpoints for. That is, like points in the training regime all the way up to the final product. And that's an opportunity for us to explore how structures and capabilities emerge during the course of learning. I'm going to employ two modes of investigation today with these Pythia models, and I think each one reinforces the other. The first is what I'd call targeted behavioral evaluation. This is the idea that we're going to use behavioral indicators to get an understanding of what kinds of representations models have learned. And here's a quick example. On the left, I have one of these language models processing the sequence, "the man in the room." And as I said before, we can look at the distribution that this model determines over the entire vocabulary given this input. And then for these evaluations, we'll generally want to focus in on the relative difference between the probability of just two of the items. In this case, I've chosen is or are. Assuming this is a good language model, it's going to have a higher probability for is as the continuation over are. And we might infer from that that that's because of this singular NP in the head position of this subject noun phrase. We then do the same thing with the same model, now processing the men in the room. And since we're assuming it's a good model, the model is now going to have the opposite preference. It's going to predict a preference of R over is. And we could infer from that that it's not distracted by room here, the closer singular noun, and does in some sense know that the head of the phrase is men. And if that pattern holds for lots of different inputs of this form, we might infer that the model in some sense knows how agreement functions, and that might begin to imply all sorts of things about constituency and headedness and so forth. Now, BLIMP and SyntaxGym are wonderful projects devoted to investigation in this mode, and for today I'm going to focus on SyntaxGym. That resource has a bunch of different conditions for various phenomena: number agreement, reflexive agreement, negative polarity items, garden path effects, some information about subordinate versus main clause structure, and a lot of filler gap dependencies. And then for our own causal gym project, we actually extended SyntaxGym with one more condition for agreement, and then a lot of extra training examples so that supervised methods can be used to uncover what's latent in the representations of these language models. These projects are both highly extensible, and what I've essentially done today for this talk is extend causal gym with a PiPP condition so that we can come to an understanding of the extent to which models know things about PiPPs at various levels. Before getting to PiPPs though, let me set the stage with a few other results from more familiar conditions to give you a feel for how these analyses work. So here I've got a plot for accuracy on these tasks. I've got model size along the x-axis ranging from 70 million parameters to the 7 billion parameter size. There's a line down here showing random chance for each task, which is always 50%. And then each one of these panels is going to show you a bunch of task results and then an average across those tasks as a darker line there. So in this case, we have 3 or 4 agreement tasks and then the average. And you can see for this task, models are doing well at these agreement things. The smallest models are not great, but the largest models have really fully solved all these agreement tasks. For NPI licensing, it's a similar picture. For gross and syntactic state, that's like distinguishing subordinate and main clause, as I said, they're also pretty good. Long distance dependencies are evidently very hard for the small models, but the large models do really well. Although you can see there's lots of variance across the different conditions in the space of filler gap dependencies. But overall, it looks like these models are quite good at these behavioral evaluations, and that might lead us to infer that they have robust knowledge of these phenomena in some sense. But we would like to go deeper than just these behavioral indicators. It could be that the behaviors are more superficial than we thought, or maybe they aren't powered by anything like what we would regard as a robust and meaningful theory. So we should try to go deeper. And to go deeper, I'm going to conduct what I call intervention-based internal analyses. Now, for analyses like these, we can start with a symbolic linguistic theory. And to give you an indication of that, here I have just a basic sketch of a theory of subject-verb agreement in English. And the idea here is that I'm proposing with this theory that the feature value for number on the subject head needs to agree with the head of the main verb phrase in its value. That's the subject-verb agreement idea. That's the core of my theory, and I might expect that any agent that's good at subject-verb agreement, like the LLMs we just saw, would have implemented a theory like this in some fashion. The behavioral evaluations I showed you are consistent with this, but what I would like to do is get some more direct evidence. And to get that kind of evidence, I'm going to again have my LLM process 2 examples, the singular and the plural cases. And in this case, the plural input is predicting a preference for R over is, which is good news. Now I'm going to hypothesize that, for example, this representation here encodes the number feature on the head noun of the subject. And if that's correct, that hypothesis, then I should be able to literally copy that representation over into the corresponding place in the plural example. And that should change the model's preference so that it now predicts as though it were a singular case. And if I can do that, I have one piece of evidence that the model in fact does implement that symbolic feature at that particular point in the model. And if I can do that for lots and lots of cases, then I have very strong evidence that in fact this representation encodes this feature in a modular fashion. And with causal gym, we essentially enable people to test hypotheses like that in a quantitative way. And here are the results of one such test. So I'm going to be working with the 2.8 billion parameter model. And you can see here that it gets 97% accuracy on the behavioral evaluation for this agreement task. To understand these diagrams a bit more, just note that I've taken the language models that I've been showing you, and I have flipped them so that it's easier to read the examples. But we still have a grid of representations. It's just that now the input is along the y-axis here, and the layers extend across the x-axis. So basically, I took the example and I rotated it, and then I do the same thing with the other example, and then I perform one of those interventions. And what you're seeing with the dark purple bars over here is my success in performing an intervention like this at that point in the model and actually getting the model to change its preference in a way that conforms to what I want from the behavioral evaluation, which could be switching from a preference to is to are, or the reverse. The darker the color here, that means that I've had more success in the causal sense, that I actually changed the model's predictions in the intended way via the intervention. And I think overall in these pictures, you can see a very clean theory of agreement, right? So here I'm showing two conditions: prepositional phrase distractors on the left and relative clause distractors on the right. Those intervene between the head noun and the point of agreement. For both of these, the representation above the subject noun is highly causally impactful. And we also, of course, get a lot of causal efficacy right where the prediction is made. And so in essence, what we get is a picture that looks strikingly like the symbolic theory that we started with. Once the model has figured out what the number feature of the subject head noun is, it has a very strong expectation that any verb it produces should also have that feature. Let me show you actually one more preliminary case to help contextualize the PiPP results. These are going to be filler gap dependency cases involving direct objects. But the logic is going to be the same as with the agreement cases. So as an example, here's our non-gap case. I know that the lion devoured. We assume devour is obligatorily transitive, and so the model should assign higher probability to the as the continuation of a direct object than an adverb like yesterday, which might indicate that there's no object coming. Our gap case is minimally different. I know what the lion devoured. That's a likely discharge site for the gap, and so we expect a preference for the adverb over the start of a direct object, beginning with the or something. So that's the behavioral test. The intervention-based test will now say that we could take some representation from processing the gapless case and place it into the gap case. And if that has the effect of reversing the model's preference for the and yesterday, then we have in effect made the model think it is processing a gapless case when it had a gap input. And if we can do that a lot in aggregate, that's going to lead us to very strong evidence that the representation we targeted actually encodes this filler gap feature. And of course, we can do the reverse as well to make a gapless case seem like it's one that has a filler gap dependency in it. And here's the summary of doing this with causal gym. I have two conditions here. On the left are single clause cases like my friend reported that or what the uncle forged. And on the right, we have cases like we all know that or what the delivery boy stated that the pilot described. In both cases, we get very strong causal effects on the filler position. That's evidently a major cue as to the dependency. And then for the multi-clause cases, we get two really interesting things. First, we get effects at potential gap sites. It's as though the model is trying to consider discharging the dependency at each one of those places. And even more interestingly, we consistently see these strong causal effects on functional elements, which seems like evidence that the model is tracking the long-distance dependency through some local steps, especially through steps that connect with the kind of the spine of the tree between the filler and the gap. All right, with those effects in mind, let's turn now to the star of the show, PiPPs. And this is going to look remarkably similar to the effects that we get from more traditional filler gap cases. Here's the logic. We have a PiPP sequence like happy though we seem, and we can compare the probabilities of a comma, which is consistent with the PiPP construal, with an adjective like happy, which is basically not consistent with the PiPP, at least for a single clause case. The corresponding PP example is though we seem, and here we expect the reverse preference. We should really get an adjectival complement to seem and not get a comma. So that's the behavioral test. We can also hypothesize that the filler gap feature is localized in a particular place and then test that hypothesis by performing interventions to see if we can get the PP case to think it's a PiPP case. And of course we can do the reverse as well to try to get a PiPP to act like a regular PP. All right, let me summarize the behavioral evaluations first. Here on this slide, I've got them broken down by one clause on the left and two clause cases on the right. The picture is remarkably similar for the two conditions. The smallest of the models are really only at chance on all these behavioral evaluations of PiPPs. My guess is that they simply haven't seen enough PiPPs in their training, and maybe they have too little representational capacity to really master them. But when we get to the larger models, even just 1 billion parameters, we see really impressive performance for both the one clause and two clause cases, with performance at both peaking at around 84%. And this is really striking and eye-opening, especially for the two clause case, because as I said before, I was only able to find 58 two clause cases in all of C4. I think the Pythia training set is somewhat larger than C4, but it still has only seen almost certainly a vanishingly small number of multi-clause PiPPs. And yet nonetheless, the model seems to have successfully learned to track the dependency that those constructions manifest. This is really striking given the paucity of evidence. And we can deepen this result by doing some of that causal intervention-based work. Here again are pictures of the single clause and two clause cases using both the Pythia 2.8 billion parameter model. And the pattern is strikingly consistent. So first, we get a major source of causal effects on the prepositional head of the construction in both of these conditions. And I already think that is really telling. If you think about left to right processing, when you encounter the preposed phrase in a PiPP, it's actually not fully clear that you're in the PiPP construction. That's still compatible with many continuations. It's only when you hit the prepositional head following the preposed phrase that you really know you're in a PiPP construction. So from that perspective, it's not surprising that the prepositional head would carry so much weight of the construction. And I think that also helps us see why the prepositional heads could be unusual in PiPPs. Why, for example, that as could take on a concessive sense, and why the prepositional choices would be so narrow, right? They have to carry the full weight of the construction, and in turn they play a major functional role in the overall nature of the construction. And so from that perspective, I think it's not surprising that we narrow the options for them because they really need to perform this functional signaling role. The other effect I want to call your attention to is that once again, for the multi-clause case, we have exactly the kind of local tracking of the dependency through the functional elements that we saw with the filler gap constructions. And to me, this suggests that there might be commonalities in the way this feature is being tracked inside these models, even across these two very different constructions. And if that's true, it's a plausible explanation for why models are able to be so good at PiPPs, even though they get almost no evidence about them. If they can just make the inductive leap that PiPPs are like more frequent filler gap constructions, then they suddenly get a lot of information about PiPPs via this information sharing across the constructions. They can effectively bootstrap their way toward a picture of PiPPs, even though they don't get much direct evidence about them. And I think that's why models are able to be so successful, even though they experience so few cases of PiPPs. And plausibly, that is an explanation for why we are able to be successful with PiPPs, despite a real paucity of evidence about them. All right, let me just summarize actually these themes about PiPPs before moving on to some discussion points. First, on the behavioral side, these LLM probabilities reflect the PiPP prepositional head effects and the filler gap nature of the construction. And that shows us that even very simple learning mechanisms suffice to create those behaviors. Second, in terms of the internal features, for LLMs, the prepositional head is a defining feature of the construction. It has real causal efficacy. And the long-distance dependency is tracked as it is in other filler gap constructions. I think this is remarkable because, again, for LLMs, as for us, PiPPs are vanishingly rare, and we get almost no evidence about them. But we now know that very simple learning mechanisms suffice to master their core aspects, even with no evidence. And I think this is plausibly because LLMs and other agents learn to share information from PiPPs, from other filler gap constructions, back and forth. And that leads nicely into some high-level discussion points. And just quickly here, first, the distinction between neural theories and symbolic theories is often discussed and debated, and I hope we can start to see that there is frankly no issue here, and that should lead us to take a more expansive view of these issues. Here is a sketch of a symbolic theory of number agreement. I showed you earlier that I can find counterparts of this number feature in the numerical representations in LLMs, and those two kinds of representations have essentially identical causal roles, up to some fuzziness with the LLM. Given that their causal roles are aligned, it seems to me that I can talk about the feature in either way, symbolic or neural, without any loss of accuracy. We should acknowledge that these features are aligned in this way and judge these ways of talking and thinking by their scientific value, because fundamentally there is no reason to think that they are in opposition. And by the way, the same relationship is going to hold with respect to this feature here and our mushy brains. And when we get to our brains, we're going to be confronted with the same questions of which levels of abstraction we want to operate at. And I would just urge all of us to embrace all these ways of talking to the extent that they can help us with our scientific investigations. I also think we could step back and kind of reassess classical poverty of stimulus arguments in light of what LLMs are able to do. LLMs acquire really rich knowledge of infrequent and idiosyncratic constructions. I showed you that with the preposing and PP cases throughout this talk, and I think you also see it in lots of other constructions, long filler gap dependencies and so forth. Those examples are very rare in the data, but models have acquired substantial knowledge about them, right? And they do that even though they have a very meager set of experiences about them. Now, that's always interesting, but the really wonderful thing about LLMs is that their learning mechanisms are entirely known to us. And so in particular, we know that those learning mechanisms don't include any inbuilt information about these constructions. They have learned them simply from those imitative mechanisms that I described before. And that shows that there is no logical requirement for such inbuilt mechanisms. It could be that humans are very different and rely on such mechanisms, but you can no longer just appeal to the distributional evidence to support such a claim. You need to make a different kind of argument. And on the positive side, this is incredible as a discovery. It was not at all obvious before that the distributional evidence was this rich. But now that we have LLMs, we can see that it in fact hides lots of really important information latently encoded about the causal properties of language, just waiting for devices like LLMs to extract it. And that is an incredible finding about the richness of this record. And finally, kind of transitioning into the end of this talk, I've been arguing that LLMs are tools for developing linguistic theory. I just want to reiterate, LLMs trained on enormous amounts of distributional evidence evidently induce lots of abstract features and relations as part of that training process. And so I think we can ask, first of all, what kinds of abstractions are they learning about key concepts like categories, constituents, anaphora, filler gap dependencies? I think my investigation confirms some core things about PiPPs that maybe we already believed about the theory, and we now have a rich new vein of evidence in support of them. And in addition, I think LLMs could teach us about new abstractions that models might be learning that could inform our theories. For example, my investigation of PiPPs suggested that the head is a highly construction-specific set of items, and I think that helps explain why it has a special status. And the bottom line here is that we should be open-minded about the idea that a successful device like an LLM, exposed to massive quantities of distributional evidence, might be better than we are at uncovering the true latent abstractions. And in that sense, they could be wonderful tools for us in developing theories. I want to emphasize that in this scenario, the LLM is not the theory, it is a tool for informing the theory. And my overall claim, as I said, is that they are extremely useful tools for that kind of theory building. I think they can unlock entire new techniques and rich new veins of evidence. All right, to close, let me give a big thank you to the many people who have helped me with the material in this talk in various ways. The list is very long there. I hope I haven't forgotten anyone. I also want to give a special shout out to Aryaman Arora, who created Causal Gym, which made it really easy for me to do the PiPP analyses that I reported on in this talk. And Causal Gym sits on top of PyVine and Syntax Gym, and so a big thanks to the people behind those projects as well. And thank you all for listening. I am extremely eager to hear your thoughts and comments.